Good morning, class. Today is 2021, May 22nd. Welcome to the third week of EngTech 4FA3 class. How are you guys doing?
Good. How about you, sir?
Very good. Just so sick of the lockdown. Hopefully more people get a vaccine so we can go out soon. How do you like FDA so far? Any complaint, comment?
It's a bit very attention to detail subject. You can make a small mistake and don't even know it.
That's life. Yes.
Professor, I have a question. I don't know if you have time now or maybe after the lecture.
Maybe after lecture, because I have a certain agenda I like to follow, or unless you have a very short question, I can do it in a couple of seconds.
Yeah, it is a very short question. It is
Okay.
about a free body diagram of the forces.
Free body diagram of forces.
Yeah. So,
okay, what about it?
So in your class example one, you did free body diagram of the forces.
Yeah.
And you ignored the forces on node one, and so we always ignoring the forces on the node one.
No, I should put it there. I didn't label it.
No. You put the forces on node one based on the forces on other nodes, not the actual forces that are acting on node one.
Okay, when there's a free body diagram, if there's elements with two nodes, if I have force on one node, there will be same force on the other node on the opposite side. Why? Because they must balance out. If not, that element's gonna fly. They must have a.
Yeah, I get that point, but we are changing the forces on node one, right? Always, not on the other nodes.
I do not remember what node one is. Maybe after class we can go through that.
Yeah, sure.
Okay. Now let's back to our class. Okay. Today's agenda, I have 4 things I want to talk about. Number 1, you guys did well, quiz 1, but I like to go through that with you, tell you what I'm looking for when I mark your assignment or quiz or test. Number 2, I like to review because last week I went through the minimum potential energy notes quickly. I like to briefly go through it one more time. And number 3, I'm going to introduce you a new friend. It is the beam element, okay? It's a new element we're going to learn. And number 4, I want to briefly introduce answers to you. And I want to briefly talk about what is our plan for the midterm test, okay? That will do. Okay, so now let's work on the quiz 1 together. Okay, you guys did very well. I mark it, I'm very impressed. Okay, the first step, when you see a diagram like this, you may, if you feel comfortable, work on it right away. If not, we draw the whole thing into string elements. Okay, now, and then name them. Okay, in this case, there are 5 elements. Okay, I am so nice right here. Okay, in the quiz, I already labeled the notes for you. Okay, but sometimes I don't do it. Okay, it's a first quiz, so it's kind of a given. But usually you have to name your own notes. Okay. Now, and then find out the local matrix. Now, in this case, K1, 2, 4, 5 are the same. 1, 2, 4, 5, which is A E over L. 10" squared times E. What is E in this case? 1 E6. Okay, double check. All units are the same. You know, this is inches square. This is PSI. Perfect. I don't need to convert anything. Okay? Length, which is 10" long. So we cross out each other. So K1, 2, 4, 5 is 1 E to the 6, 1, 1, negative 1, negative 1. That's the local matrix. Okay, if you feel comfortable to put it into the global matrix right away, it's good. But in my question, I asked for the local matrix, so you must specify that. Okay, sometimes I do, sometimes I don't. You know, depends on the questions. For K6, sorry, K5, K3, K3, A E over L, which is 20 times D6 over 10. 2E6. K3 is a 2E6. Okay, by the way, this is how I prefer to write it because it's faster. This is equivalent. Okay? Up to you how you do it. As long as I understand it, as long as you can present your data, it's all good. The next step, we need to assemble them globally. Global matrix. Okay. So whenever they share the same node, whenever they have the same degrees of freedom, you can merge them together. I like to factor it out. Okay, so I can say 1 times 10 to the 6 right here. Okay, and then this is let's look after 1, 2 as well. There are K1 and K2. Will be 1 plus 1 minus 1 minus 1, 1 plus 1 minus 1 minus 1. Okay, so this part is done. All right, then look after the second mess, second portion of it, which is a K3, which is a 2. Wonderful. And then finally, the rest of it is plus 1 plus 1. Okay, is it good? Hello?
Yeah, okay.
All right, then I have to assemble the displacement factor. There are 4 nodes to display, to move. And on the left side, I have forces to deal with. Okay. U1 and U4, they're fixed together. Okay. U2 and U3, they're moving. Moving by how much? I don't know. On the left side, F2 is 10 pounds to the left. F3 is 20 pounds to the right. Okay, F2 is, because it's to the left, so it's 10 pounds to the negative 10. F3 is 20. Okay, if you have that, you already get like 80% of the mark. Okay, I count every single step. If you just give me the answer right away, you won't get you much. Okay, but I count the steps. I want to see how you think, how you process the problem. The rest of it is very easy. You just multiply this part. What do you get? Okay, you got two equations. U2 times 4. I think it's 4. Yeah, that's right. Minus 2U3. Did I do it right? I think so, yes. Back to the comments to one of the students. It is attention to every single detail. Okay. Because when you're building something, building a bridge, building cars, like if you miscalculate something, you might kill some people. But luckily, when you are working in an engineering firm, when you have a job, you don't work by yourself. You do a problem, you have an assignment, you work on it, and some of your colleagues will verify it for you, provide feedback, many gates before you issue the document and build something. Anyways, right here, you have two equations, two unknowns, and you just solve it. Once you have U2, U3, you can calculate the reaction force. Reaction force on F1 and reaction force on F4 as well. Okay. So overall, you did very well, and I'm very impressed. I'm looking forward to mark your quiz number 2. Okay, I'm gonna move on.
Chris, I have a quick question.
Yeah, what is it?
So in this, if we were to mark the directions of U2 and U3, how would we do it?
Sometimes, instead of 10 pounds, let's say I'm 10 inch, and right here is 20 inch. Okay, so I do not apply boundary condition anymore. Okay, I'll be applying negative 10 inch. Is that good? Sometimes you're allowed to do so. On your left, you always apply boundary condition on forces. Okay, on the right, you can apply boundary condition on displacement, inches. Did I answer your question?
Yeah, I would say, but I was just thinking about it from the, let's say if we go to that spring element diagram, if you go, if you move the page up a little bit.
Yeah.
Yeah, and that, so in the examples we did in class, right? So the forces were going all in one direction, so the U's were also going all in one direction. Now, let's say the force 10 pound is going to the left. Does that mean U2 is also going to the left in this case? Just thinking.
I let the equations decide for me. If yeah, I don't know U2 is moving left or right yet. Okay, I put in the boundary conditions, and I let it decide for me. When a U2 is a negative, then you move to the left. If it's positive, you move to the right.
All right, it makes sense. Okay.
Okay.
Yeah.
Okay, I like to quickly go through the minimum potential energy approach lecture again. Okay, won't be long. So we start with 1D element, okay, and then it has two nodes. Note 1 and note 2. What's going on with the note? Each note, you're allowed to apply a force to it. One direction only. Oh, sorry, like one along x-axis. No, not necessarily one direction. You can move both directions, but along one dimensional. And it's allowed to move left or right as well. Same here on note 2. You have a force, and you're allowed to move as well. So this element, each note has 1 degree of freedom because it can move left or right. But the element has 2 degrees of freedom, DOF. I know what's going on the note, but what is going on in between? I need a shape function to decide for me. So I put everything in terms of u as a function of x. So x can jump from 0 to L. Okay. So I assume a constant.
What does C represent?
Constant.
Oh,
it's a constant. It's something I don't know. I just use C1 and C2 right here, but very soon you'll see. I don't need a C anymore. It's all disappear. So I put that in a matrix form right here. So far, I just assume 2 constant. Now I apply the note condition. When x is 0, I know it's moving U1. Because this is something that I know. I know in note 1 is moving note 1 is moving U1, note 2 is moving U2. Okay. So I apply that C1 plus C2 times 0 is to U1. And then when x is L, I know it's moving U2. So again, I apply the same thing here. We got U2. Factor out C1. Okay, C1 is something that we're looking for. And then I inverse the whole matrix, whole mess. I get this. At times the matrix, I get this. Basically, this is the shape function, which is 1x, so the 1 and x times, this is C. Oh, sorry. This is C1, C2. All right, put this aside. We want to study the elastic behavior within the elements. The work done deform uniform force. The work done within an element is force times the total displacement. But right here, my intention is to put everything in terms of the strain. Okay. I start with the work done. And then I take the integration of it. And I put everything in terms of a string energy, string. So in total, the energy stored within one element is this, but the energy stored within the whole system is this term. My plan is to store the energy, store energy in terms of string. Okay, then from the string I want to develop the string displacement relationship. That's another important step. So I take the derivative of the shape function. I get the string displacement matrix. Okay, string square, and put it in terms of the string displacement matrix. So finally, you put everything back to the previous equations, get this term. And you factor out EA. If you factor out EA over L, factor EA over L, the whole all the equations get you the stiffness matrix of the spring element. It is kind of, say it again, sir.
U also constant?
In this case, U is as a function of X, still is a function of X, okay? But it's kind of funny.
We're not doing any integration on it.
That's right, we're taking integration of a U. In right here, you know, it's not a one constant. U can be anything along the x-axis. But it's funny, you know, we're taking the derivative of the total energy with the U, which is a variable. It is not easy to understand the whole steps, you know, all the details, because seriously, you know, a project like this is worth like a PhD degree. You know, it takes many years to develop that, but we are the lucky ones. Someone developed for us, we just use it. Okay, but the major concept is like this: you start with elements, you develop that into shape function. From the behavior and the energy equations, you put everything in terms of strain. Okay, and with the strain, you develop a strain and displacement relationship, the matrix. You put in the equations. You take the derivative. You take the derivative of this and factor out EA over L. You get a stiffness matrix of the elements. And the work done on that assembly can be calculated by integrating Fx and Ux. Okay, because Ux is variables, right? And then the shape function of that which is the shape function. The variable, okay, sorry, the variable u is shape function times the u vector that you know. Oh, by the way, I think I said something wrong. I previously said u is not a constant. It is a constant. It is u1 and u2. Known values that we define in the first step. Okay. How much they move, u1 and u2. Okay. Anything along the axis, that's variable. Okay. But u1 and u alone is something that we know. Okay. And from the examples, we don't need to develop the stiffness matrix anymore. We just use it. We know the stiffness matrix is a k, and negative k, negative k. Okay, but we only have to define the force, which is the applied force, 10 pounds over per inch, times the shape function. And the shape function of the elements we know. We learned it previously. Each element has this unique type of shape function. Okay, for that shape function, you can only use it in a 1D with 2 Noether elements. Okay, do not use this shape function for some other elements. You cannot. Okay, each element have this unique shape function signature. So it is a 1D with 2 Noether elements. So we use the shape function and take the equation of that. We get the force on the 2 nodal points. For F2, this is the second portion of it. And then we take the shape function of it. And then we integrate that. We get another force. We put those 2 forces together.
Sorry,
Yes.
so this F1 and F2, they are work done?
They are, F1 is the local force matrix. Let's call that local force matrix. F1. This is local force matrix. F2. Okay. That applied force, okay, is gonna doing something to the elements, right? The applied force is doing something along the elements, but what are they? With this expression, we can calculate what this force is doing to the elements on both nodes. Cool. So this is the local. What happened local in a matrix, right? Locally on each elements. When we combine them together, we get this. And then we apply the boundary conditions. We get U2, U3, and then reaction force along the wall. Anyway, I have designed a new quiz for you, which is related to this topic. And after the quiz assignment, you will learn a lot more, and we'll go through them in the future. Is that good? Any questions on minimum potential energy so far?
Can you just explain for this this example how you set up your S matrix?
Stiffness matrix?
Is the S matrix the one in?
I thought S matrix was the shape function.
Or
Yeah.
that's the strain displacement matrix.
I do not need the strain displacement matrix in this case because I not
The x minus x squared over 20. What is that part? That's the st, right?
yeah. Well, for the shape function
It's
for
the
the
sorry, it's the shape function. Yeah.
shape
Can you
function for
explain
the
kind of?
shape function for the string for the spring elements is given. It's always the first term 1 minus x over L. And then second
You
term is
said
x over L.
okay.
This is always the case.
You
Always.
said for more complex ones, it's going to be different though, right?
The more complex one is the strain displacement matrix, is that right? In this case, we don't need it because I already know how to calculate the stiffness matrix for the string element. I don't need to go through this string elements matrix and calculate the energy again because I know the string elements matrix will be like this, right? So I don't need to calculate it one more time. So I just use the shape function, which is what 1 minus x over L. The shape function.
So this is for two nodes, right? So if we have three, if we're gonna do a shape function for 3 nodes, it's gonna be different, right?
Very different. Very different.
Okay. But we like you showed here, we don't need to do for complete 3, right? We can divide it into 2 and then combine it.
It's a lot easier, isn't it?
Yeah.
Right.
Yeah.
Yeah, I know. Did I show you examples? Yeah, I saw that in a textbook. You assume ux and then what is c1 plus c2x plus c3x squared, something like that, right? I saw that in a textbook, but I don't want to use that. This just takes way too long. Well, if I have an element with 3 nodes, why not join 2 elements with 2 nodes in it?
So it works with the like any number of elements, right? Say we have another 0.4 also, so we can divide it into 3 different elements with 2 nodes.
Yes, you can do that. Yeah.
Okay.
With only one condition though, they must have a common degrees of freedom. You understand what I mean by that?
So even if the applied force is changing, is it okay?
Applied force is changing along the element. Yeah.
Yeah.
As long as they have the common degrees of freedom.
Okay.
Right here we have force 1, right? And force 2. I joined them together because 2 and 2, they are the same. The same degrees. But if you have F1 and then two and 3, this is F2. You might have to think twice, you know. This one, yes, you can join them. This one, you have to study further. How do I join them together? Do they have the same degrees of freedom? Because this one is moving like this, right? This one is moving like this and that. That's another trust element problem. Any more questions on minimum potential energy? There will be a quiz or assignment today on this topic. I can give you a hint. You know, basically, you don't have to deal with the strain displacement matrix at all. You know, all the development for the stiffness matrix is already done. You don't have to go through that integration derivative mass right here, but you must understand it. Oh, by the way, I have some comments on the on your quizzes. Okay, the quizzes is not taking a long time. It's like maximum 20 minutes, half an hour for each quiz. Right? Do not wait till the last minute to do it, because our course is getting easier in the future. When the answers come up, you will be easy. So when you have assignment, don't wait till last minute, because my quiz is due always on Friday, right? I would say more than 80% of the students, they hand in the quiz the very same afternoon. So yeah, just a comment, don't wait till last minute. If you have time, work on it. All right, I think that's good. Let's work on a new element.
Sorry, sir.
Yes.
I have a quick question about the global matrix, where you develop 50 plus R and 50 minus 50. Can you explain, like, how do you get that? Please.
Oh, no problem.
The example.
Yep. You talk about the force matrix, right? The force.
Yes. Yeah, the force matrix.
Do you have problem? Do you understand the
Yeah,
integration?
yes.
You have the integrations, right?
Yeah.
And do you understand this part?
Yeah.
Then that's
Oh,
very easy. That's very easy. I'll show you. Okay. Right here. And then this part.
Oh, you just brought it down. I
just goes to
see.
right here. Okay, is that good? Can I move on?
Yes, thank you, sir.
No problem. Yeah. Okay, today I'd like to introduce a new elements to you. That element also has two nodes. Okay, node I and node J. However, it behaves something very different. Each node, they can move up and down, and also it can turn. It's allowed to turn. So that's why the element has what? 4 degrees of freedom. It has 4 ways to move. So because it has 4 degrees of freedom, we introduce 4 terms to it. C3 and C4. C1, 2, 3, 4. Okay. To define how much it turns, we can specify the degrees, the radian, but there's another way to do it. We define the slope by using the rise over run. So we take, if the deflection along the if the deflection perpendicular to the beam is small enough, we can take a derivative of this, of that previous term. So you get this, okay? So this is term with the slope. Oh, by the way, usually when I want to deliver a lesson to you, right, I like to write out the whole note. But because the beam elements lesson, right, the lecture has a lot to write, so that's why I just pull up the note and mark it up. I hope you're okay with that. This is too much writing, so I just mark this up. Do you mind? Okay. After we Yes,
Sir,
sir.
what is that function? Is that a V or a U on the beginning in front of the C1?
It's a
On the
V.
first line, it says let. Is that a V or a U?
It's a V.
Function of X.
It's a V. Here. Yeah, it's a V. The actual displacement is U. Hey, buddy, good comments though. Maybe I should change that in future. You know, yeah, you're right. Okay, in this case, you know what? The function is V. The actual displacement is U. Okay. Good feedback. You know, I might change that in the future. But in the meantime, let's assume the function is V. The actual, all the information we know, UI1 and UI2, UJ1 and UJ2 is U.
And one more question.
Yes,
Does that small v represent the velocity?
no, it's not. The displacement, the actual
Only the displacement.
of
Okay.
the on the node. Okay. What it does is we know what's going on in the node. But what about something in between? That's the V function. How much they move along the L. X is from 0 to L. Questions, comments?
All good.
It's all good? Okay, I'm going to move on now. Okay, now we know, okay, for node I, X is 0. So we put all the X to 0 and you got C1 and C2. So right here, we know UI1 will be C1 and UI2 will be C2.
For this example, why do you choose to use 4 C constants? Why is 4 the magic number here? 4 degrees of freedom? Is that what we're looking at?
Exactly. 4 degrees of freedom, 4 terms. Okay. Previously, the string element is 2 degrees of freedom. So x c1 plus c2 x 2 terms. Very good question, very good feedback. I like that. Yeah. 2 degrees of freedom, 2 terms. 4 degrees of freedom, 4 terms. Just want to let you know in the future, you can learn a 2D elements, which has 6 degrees of freedom. And guess what? 6 terms. That lecture is a mess. You know, but you must understand what we have so far. We must understand string elements. We know beam elements. Then I'll introduce a more complicated elements to you in the future. Okay, let's move on. Okay, for node I, X is 0. For node J, X is L. So we substitute X equal to L to these equations. And when X is L, we know UJ, okay. At the end of it is a UJ1 and the slope is UJ2. Hello, I want to do an audio check. Can you hear me good? Because I think the internet is unstable for a bit.
Yeah, it's good now, but just
Yeah.
about 10 seconds ago, your voice was breaking up. I thought it was only for me though.
I hate COVID so much. It's so much better to do that in class, in person. Anyways, we have assumed two functions, the Vx and the dVx, and then we apply the boundary conditions when x is 0 and x is L. Okay, we get this and that. Do you have any questions up to here? Okay, I'm gonna move on. We just repeat the same recipes. We factor out C1 to 4. And right here, this is the known displacement. We take the inverse of that, which takes me so long. But you know what? I'm gonna I did that for you. Okay. We put that inverse matrix to here. We multiply that together. Multiplied it together. We get 4 shape function term. This shape function term is so long, so I write it separately. X1, S2, SJ1, and SJ2. Okay, guys, remember this is the unique shape function for beam elements only for beam elements. This shape function will not work in other elements, only for beam elements. Okay, let's move on. Okay. Bending theory. Let's talk about bending theory right here. Okay. When this is a beam, when you bend it a bit, there will be a small changes to this axial length. That makes sense, right? Because when this is the original shape, when you bend the beam, it's a bit shorter, right? So let's define that by Ux. Okay, and from the bending theory, depends on how much you bend by Y. And then you can develop that bending theory. So we have that dV functions. Okay, so again, the main thing right here, why did I do this? What's wrong with me? You know, I was writing shape function, and all of a sudden I talk about bending theory. Because what? I want this term, the string energy. String is so important in terms of energy. You know, we move it. We move by certain length, okay? And then the energy will be stored in between. And that's why we need this term, the string, okay? And which is the du over dx, the total length, dx, okay? We take the derivative of that, and when we apply bending theory, we put this term term and take the derivative one more time. And since previously we have a function for v, so we simply take the shape function and take the derivative of it twice, 2 times. Did I confuse everyone? You guys still there?
Yep.
Yeah, for 1 second, I thought everyone just dropped out. Please stay. I promise you will love FEA.
No, you could.
Thank you. All right, I'm gonna move on. Okay, I have shape function, and then because of band theory, I can get the strain energy. So sorry, strain of the elements, and then I take the derivative of that. The shape function we have, we'll take the derivative twice. Okay, we get 4 terms. Same recipe. We use the strain energy stored within the elements. Can we substitute? See the key components right here. It's a strain. Okay. We know E. Oh, I is the moment of inertia. Okay. Again, it's given. It's constant. It doesn't change along the beam. And we factor out this term. This is going to be the stiffness matrix for a beam element. Okay. By the way, D is a 4x1 vector. For D transpose times D will get you a 4x4 matrix. It's so long, we have to repeat that. Let's do one entry, you know. This is the first term from the D vector right here. See? Okay, that's the first term. This times this together, we take the integration of that, apply the boundary condition from L to 0, we get 12 over L cubed. Repeat that 16 times. You get the stiffness matrix of beam. How are you doing so far? Okay, in all my problem sets, quiz, exam, you don't have to show me the development of it, but you must know how to use that matrix. The condition is this matrix only works for one beam, okay, with two nodes. It moves up and down, doesn't move. Moves the elements, the nodes moves up and down. It doesn't move left or right. Okay, it cannot do that. Only up and down, and it turns. Just to recap, this is 4 degrees of freedom beam elements. Okay, this is the stiffness matrix for the beam elements. But what about the loading factor? Let's say work is being done on the beam elements. Okay, we apply the same recipes, dF over U. We had that in the previous lecture. Okay, the work done. This is a shape function, and this is U that we know. Known displacement. We have the shape function, we transpose it, and then we take the integration of that. Finally, we apply this. From L to 0, and we get 4 terms. Okay, this the uniform load applied on beam. So for all the talk I had, we developed the stiffness matrix for the beam elements and the loading vector. When there's a uniform load on top of the beam. Note, the uniform load on top of the beam is applied perpendicular to the beam. Okay, it doesn't work when you have force like that. Okay, you can't apply the force actually on the beam. I know you're confused. Don't worry, man. Let's work on an example. You will feel better. I have a beam, okay, which is attached to the wall. It has certain length, okay, and there's a uniform load applied to it, 100 Newton per meters. Okay, we have the constant elasticity, and also it has inertia. Okay, so find the deflection at the end of it. This equation, this matrix is given. Do not develop for me in an exam or test, unless I ask you to. But usually, you just have to know, you must know how to use it. Do not develop it. Okay. And we know the L is 1 meter. EI is 100 times 10. By the way, make sure they have the common units. Pascal is Newton per meter square, which is good. Okay, common unit. Sub in the L, we get this term. Okay, that's the stiffness matrix, the K matrix. Apply force. That comes interesting. These things already given. Okay, you just times that by 100. Oh, by the way, it is already given the integrations there. Yeah, right here. It's the given equations. In the test, you don't have to do this, it's already given. Okay, right here, I just I repeat the integration again to show you how I got it. Okay, you can study it, but you don't have to do it. Okay, because P right here, pressure is negative 100. What is the L? It's times 1 meter divided by 2. Right here is, again, P is negative 100 times L squared divided by 12. The first term is a negative 50. The second term is a 100 by 12. See, that's what I got. It is a given equations. So let's use it, right? So we put these 4 terms right here. And then we have the stiffness matrix. We know the 4 terms, 4 degrees of freedom, which is a V1, phi 1, V2, phi 2. It's locked against the wall on note 1. So we will apply the boundary condition 0. Okay. On the left side, we know there's a reaction force and a moment acting on the beam to hold it in place. So we must do that. We must write an R1 and M1 here. And we have 4 equations, 4 unknowns. We solve for everything. Then we have V2, which is how much it deflects. And then that's how much the angle turns. Notes 2. Any questions so far? If you don't, I have a question for you. Okay. This is what we have, right? The beam. And we have a uniform load. We want to calculate deflection. What if I'm adding one more node, one more load to it? How do I handle that? Hello?
Yes.
If I have an additional load to it, the newtons, guess what? I move back to the equations right here. That's the additional load we have. Please add it to the third term. Do not add it here. Unless I say moments. Then you have to do something right here as well. Get it? Okay. That's it for the beam elements. I know it's tricky to understand everything. Try to review the notes, and you will have a better feeling of it. Review the examples. Review the example of it. So for homework today, there will be one question on potential energy equation, and review your notes on beam elements. I want to, okay, I am writing, I'm designing your midterm exam right now, okay? Your midterm exam will be based on the rod elements, spring elements, the truss elements of it, minimum potential and energy. Yeah, that's right. This one. And also the beam element. And very likely, I might ask you to join them together. What I mean is when you have a say a spring element, you know, you have no issues joining the two spring elements together, right? And you must be, as long as they have the common degrees of freedom, you can join them together to the truss element. I might tell you some more about this in the next class, okay? But anyways, so my plan is to let you review the notes, go through more examples. I want to make sure you're ready before we write the midterm test. So probably next week, I want to start my lecture on answers. Okay, so you guys can start work on the answers at the same time and study, and I'll train you up, make sure you're ready for the midterm exam. That's my plan. Any comments?
Professor, how many questions will be there in the midterm?
I haven't finished it yet, no, but that's my plan. We cover 3 topics. Midterm test will be the spring elements, truss elements, and beam. And you must know how to combine them together. Okay. But I'll give you more exercise, you know, proposed date, probably 2 to 3 weeks from now. But in the meantime, I want to go through some answers exercise for you. Okay. And you still have time to study. But okay, at the beginning of the class, beginning of our course, right? We talk about we need a Windows PC to run answers. Okay. For all the Mac user, I really hope you can borrow a laptop from your friend or whoever. and run some answers. It is a very powerful tool if you want to have a job in FEA, and it's a good skill you put in your resume. Okay, and then you can say that I've preliminary basic level on answers. That's the intention of this course, to let you run some answers on your own. Anyways, we'll go through more details, in the future. I think for today, that's all I want to say. I think we have enough lecture for today. I'll make it short, And I'm here to answer any questions if you want. But in the meantime, yeah, thank you for attending my lecture.
Professor, would you be able to post an example with all these spring truss and beam